Greetings, I am Bekir and Özel. I am a graduate student in Middle East Technical University, Department of Architecture, and a research assistant in Yıldırım University. The co-author of this paper is Mehmet Koray Pekeriçli. He is an assistant professor in Middle East Technical University. As you can see, the title of the study is Potential of Biosensors as Indicators of Safe Behavior in Construction Sites. This is a preliminary study that we hope would lead to further studies. Let me first show you an outline of the presentation. First, we are going to see some background information about biosensors. The two types of biosensors selected for the study are electroencephalogram sensors, EEG for short, and electrodermal activity sensors, EDA for short. Some basic information about these sensors and their working principles will be given. The follow-up will be the discussions on the potential of these sensors in the field of construction safety. And final conclusions will be drawn and some directions for future studies will be given. So let's start with some background information about biosensors. Biosensors are electronic devices that detect and measure states of organisms. Most of the time what they do is to measure electrical and chemical activity, but there can be some other types. The modern sensor systems allow real-time and wireless data acquisition, enabling many research and application possibilities. Moreover, they can be as small as a ring or a bracelet. You can see a sensor system in the form of a bracelet on the slide. As you see, it is not much different from a smartwatch. And since biological responses, for example, heart rate, is harder to control than, let's say, written or verbal statements, data from biosensors are prone to be less biased. The first type of sensor systems that this study investigates is EEG sensors. EEG is the methodology that is used to investigate electrical activity in the brain. And luckily we don't have to go into the brain to measure this activity. Electrodes that are attached to the scalp are used for it. You can see two examples of EEG devices on the slide. The one on the left is a full-scale system that is used in detailed measurements. And on the right there is a mobile EEG system that can be used for field studies. According to their signal frequencies, the electrical activities of the brain measured by these sensors are generally categorized under 5 bands. These are delta, theta, alpha, beta, and gamma waves. And by examining these wavebands, mental states such as low vigilance, drowsiness, or mental fatigue can be detected. And besides reviewing the wavebands, one of the most used methods in EEG research is the examination of event-related potentials. Event-related potentials are responses of the brain that can be directly linked to a specific stimulus or an event. It is a widely used method that is adopted by different fields of EEG research. And well, it must be stated that since there are thousands of neurons in the brain firing simultaneously, it is not an easy task to isolate the effects of a single stimulus. Usually, repeated instances of the same stimulus are introduced to the subjects so that the average of the responses can be calculated. And the second type of biosensors reviewed in the study is electrodermal activity sensors, EDA for short. EDA can be described as changes in the electrical conductivity of the skin. And these changes, the changes in the electrical conductivity of the skin, is a result of activation of eccrine sweat glands. And eccrine sweat glands are activated by sympathetic nervous system, which is directly related to the so-called fight or flight response. That means EDA can be used as an indicator of arousal, situational stress, and emotional response. EDA is usually measured by sensors placed on the hand of the subject. palms, fingers, and sole to be more specific. You can see two typical examples of EDA sensors on the slide. It should be noted that EDA is affected by many variables such as age, sex, time of the day, stage in the menstrual cycle, time from the last exercise, personality. Therefore, it is useful to determine a base conductivity level specific to the subject and the time of the measurement first. This base conductivity level is generally referred to as the electrodermal level, and increases over this base level are called the electrodermal responses. They are responses specific to stimuli. We can now move on to discussion on the potential of these sensors in construction safety. EEG can be used as an indicator of mental workload, and a high level of mental workload can cause an unintentional blindness towards some objects or events, such as construction sites hazards. And detecting a high mental workload would be useful in understanding who is under a higher risk and when. However, it must also be noted that the higher mental workload could be a direct requirement for the job to be done, and it can be unavoidable. Moreover, it should be questioned if it is worth the resources and effort, because EEG sensors are not cheap. An average system would cost thousands of dollars, and considering the financial and human resources spared for construction safety management is already scarce, spending this much resource for EEG sensor systems and their implementation might not be feasible, and therefore real-time measurement via EEG sensors on the field might not be feasible. A more feasible option might be designing experiments that would test AEC activities in terms of mental workload via these sensors. These experiments would reveal which types of activities result in a higher mental workload. This information can be used to understand who and when are prone to unintentional blindness towards hazards, and therefore more specialized and efficient precautions and spot-on safety training can be implemented. And considering how inefficient the current safety training is on improving hazard recognition skills, the importance of this spot-on safety training can be understood better. Another possible usage of EEG is the detection of mental fatigue before starting to work. Using EEG sensors before the work instead of during the work would make them much more feasible. And current pre-work fatigue detection methods are mostly based on expert judgment of the site manager or safety manager, and it can be said that they are neither objective nor efficient. But the fatigue can be practically detected before the work via EEG sensors, and then interventions might be possible. There are, of course, some additional problems with implementation of EEG sensors in the construction industry. The first one is the lack of expertise in EEG in AEC industry. Also, the construction environment might cause artifacts in the data, which means the sounds or the equipment used in the construction sites might cause unwanted spikes in the data. And of course, it is not an easy task to attach a high number of electrodes to the scalp and make them stay as they are. Those electrodes can slip, can fall down very easily. And finally, there are no off-the-shelf solutions for AEC industry. This is a problem, but also a natural call for research and development. The second type of sensors to be discussed is EDA sensors. EDA sensors can measure risk perception. It is actually one of their primary usages. And risk perception is already useful information to have as a safety management. But moreover, it is pointed out that risk perception might be an indicator of the real risk when the individual biases are minimized. Therefore, these sensor systems could be used as a practical and reliable method for measuring risk in real time. Nature, this is a bold claim and it requires extensive research to be confirmed. But there's a potential for initial academic research and then a follow-up real-life application. Also, off-the-shelf EDA sensors are suitable for AEC industry. Do you remember the bracelet type sensor that I showed earlier? It is actually an EDA sensor system, or let's say it includes EDA sensors because it has multiple sensors on it. And there are many models similar to this one, and some of them are water resistant and dirt repellent. They can be used in the field without much problems. They can also be worn for extended periods of time, and by extended periods I mean multiple days. Moreover, these systems are rather accessible. Their prices can be as low as $100, and even high-end devices can be purchased at $1,600. As stated earlier, there are mainly two types of data in EDA measurement. Electrodermal level and electrodermal response, and information from both of them would be useful in safety management. Electrodermal level can show long-term high stress that is independent of a quick stimulus. This information would be valuable for safety management, considering the negative effects of high stress level on safe behavior. On the other hand, electrodermal response can indicate an encounter with a hazardous situation. The information on when a hazardous situation is perceived would be precious for safety management in AEC industry, where the time and the location of the hazards are rather hard to guess due to the unpredictable nature of construction sites. Naturally, there are some obstacles on the way of implementing EDA sensors in construction safety. The first one is, again, the lack of expertise in EDA among AEC professionals. The second one is something called a non-specific electrodermal response. Non-specific responses are electrodermal responses that do not have any connection with a specific reason or a stimulus. When they occur, they might cause false positives. They are just random responses. And EDA responses can also be triggered by social interactions or thermal conditions. If the weather is so hot, or if you are having an interesting conversation, it might cause changes in your electrodermal activity. This might also trigger some false positives. Well, to conclude, current methods of understanding, monitoring, and controlling safe behavior are not efficient enough. They are exceedingly subjective and unreliable, so improved methods are required. Biosensors could help improve these methods. Both EEG and EDA sensor systems may have various utilizations and potential applications on construction safety. These sensors can be directly used on the field, either for real-time data collection or pre-work evaluation, or they can be used in safety research to broaden knowledge base on construction safety. However, implementing biosensors in AEC industry poses unique challenges, and therefore it requires unique approaches. That will be all. Here are the references for the study. and thank you for watching.